Hi, this video is going to cover when we can take a binomial model and turn it into a normal model. So what this means is everything we've been doing has been covered under this binomial section, okay? But when n's get very large, when we have very large number of trials, okay, it's a lot easier to work with this normal model than it is with this binomial model. Okay, so for example, let's talk about some problems where well, first let's say, when can we do this? When can we use a normal to approximate a binomial probability? Okay, so just by that sentence alone, that tells you that when n gets to a certain size, then the probability of x from a binomial, okay, or the probability of the x given a certain range, so the probability of x is greater than something, okay, it'll be very similar to the probability that x is greater than the random variable here. They'll be very similar. Okay, so when can that happen? So this is called a condition, and we're going to be doing a lot of conditions throughout the year, but this is a condition. So what this says is if the number of successes and failures is greater or equal to 10, then a normal model can be used to approximate a binomial model. Okay, so let me show you a case where it won't work. Okay, and here, this what this looks like. What's the number of successes? The number of successes is, I should say, the number of expected successes. Sorry. The number of expected successes and expected failures. How many expected successes are we supposed to have? Okay, so the expected successes is always n times p. So if n times p is greater than or equal to 10, and n expected failures would be 1 minus p is greater than or equal to 10, then what that means is the binomial np approximates, or the normal approximates the, it's n comma p. Let me put this real quick. The binomial approximates the normal, or the normal approximates the binomial. The two parameters you always need for those two are n and p. This is n times p, square root of np 1 minus p. That's the standard deviation of the normal. Okay, so what happens when these two conditions are met, then we could use this. And there's also, that would be one condition. Another condition has to do with our independence. And I'm actually going to do a video about why this is true. But for now, just know that the sample must be 10%, has to be less than 10% of the population. And the sample is the trials, the number of trials must be less than 10%. I'm going to do a whole video on this, so you guys are going to want to watch that. Okay, if you don't want to just know this condition. Okay, so what does this mean? Let's do an example really quick and show you why we can't do this unless n is pretty large. Okay, because if n is pretty large, then these things will be true. Okay, so say like n is 100, then this p would only have to be 0.1 for this to be more than 10. Okay, stuff like that. So when n is really large, then we always could do it. So let's just do an example where we can't. Let's say you're bowling, and okay, so let's say there's 10 frames, and the chance you get a strike is 70%. It's probably pretty high, but say there's a chance you get a strike is 70%. So actually, I'm going to make this 5 frames, just so we could see this thing. So if you have 5 frames, it's 5 times your bone, and the chance you're going to get a strike, the probability you get a strike is 0.7. 0.7. So the possibilities of strikes would be 0, 1, 2, 3, 4, 5. So what this is saying is, if once you put all these probabilities in this distribution, do you think it's going to be normal? Do you think it's going to look normal? Okay, well, it won't. It won't look normal. Okay, so this is the probability that there's no strikes. This is probability of strikes. This would be 0.3 to the 5th, and this would be probability of all strikes is 0.7 to the 5th. Now if you fill in all these probabilities, which I'm going to go ahead and pause the video and fill them in, and then we're going to see that this will not look normal at all. So I'm back. So I got all these probabilities, and this is the probability of every one. So if we were going to graph this, it would, if we were going to do a histogram, it would kind of be like this: 5, 4, 3, 2, 1, 0. And you could see the things that are going to happen the most are, the thing that's going to happen the most is 4. So this goes up to here, and that's the frequency up to 36. Okay, so that's 36%. And then this is going to be 17%, which is maybe here. And this is down to 31%. And you can see that this distribution is skewed left. So that's skewed left. So you can't use a normal on this. Okay, so let's see if our expected values hold up. So what's n times p? How many expected strikes is this person supposed to get? So this is going to be out of 5 tries. Okay, so this would be 3.5. So the number of failures would be 5 times 0.3. So this would be the leftover ones. Okay, so these are not, they are not greater than 10. And as you can see, the distributions aren't even close to normal. Okay, but what happens here is, if you did 100 frames, if we did 100 frames, okay, we would expect 70 strikes, and we would expect 30 non-strikes. So now my distribution doesn't go from 0 to 5, it goes from 0 to 100. It's kind of funny because, well, not funny, but here's the 70, 71, and here's 69. Okay, so this is this is going to be the highest percentage right here. And if you go 3 standard deviations this way, and you go 3 standard deviations this way, what happens is it actually works out. It works out that this is normal. If you could visualize a graph, okay, a normal graph, in the middle we'd actually have 70, because this is what we expect. We expect this many strikes if they took 100. Okay, but if you go 3 standard deviations this way, and if we go 3 standard deviations this way, it'll cut off at a pretty good, it's not going to go that much. So the rest is just 0. It just aren't going to happen. For example, we could find the standard deviation of this. So what would be the mean of x? I found that already. That's 70, the standard deviation, just so you can see why this thing works. I'm showing you why this works right here. Okay, so the standard deviation of this would be the square root. Okay, here's the formula for my standard deviation, which would be square root of 70, that's n times p, times, okay, which would be 30%, because that's the failure. See, this is the number of successes, n times 0.7 times 0.3. So this is standard. See the standard deviation is only 4.58. Okay, so if I went up 15, if I went 3 standard deviations, let's just say it was 5. Let's say I went up to 85. How much is this going to happen over here? How much is this going to happen? Basically, this isn't going to happen. None. Okay, so this over here kind of would be like an 85. Let's say I went down 3 standard. I'm actually going a little more than that. I'm going more than 3 standard deviations. And this over here would be 60-55. So what's happened on a binomial, it kind of looks like this, right? It goes from 0 all the way to 100 with all the probabilities under it. So what happens here is, you know, basically from 85 on, all under here would be like 0. And if I go from 55, all these would basically be 0, all the probabilities. So really, I'm only interested in this middle portion right here. Okay, and the graph of these middle portions will look normal. Okay, so now we could do our normal distribution. We could do, you know, just like we've been doing with these z-scores, and use this normal distribution. Okay, so that's when we could use the normal to approximate the binomial. And on the next video, I'm going to do a couple examples and show you specifically when we could do this and how it works, and actually how close it would really be if we actually did a binomial. Okay, and also talk about again why it's not plausible to use binomials for high ends. Okay, so be sure to check out that video for those examples. Thanks for watching.